you're
Okay.
sat now, just so you know.
Good.
Actually, since Jim is on the way, I think we're good, but can we just get a quick triple check here? Something was, the screen was like showing on the outside. Are we also?
Yeah, it was kind of
first
funny.
The moment I called you, I think it sold itself. What? Is this?
So it looks, seems okay.
Is it okay?
I think it's okay. So
What did
we had to get mirror displays and do the right screen thing.
Okay.
But it was doing some really funny stuff I've never seen before that. So
Anyway.
we'll see if it stays.
The room knew you were coming and sold itself, so I think we're set now. Sorry to.
Her dad was
sorry,
coming.
Sorry, you're coming running in. So.
Thanks for your.
Thank you, much appreciated. And I'm sure you have it. And I probably will. Actually, this entire room is on the chair, so. Okay, why don't we get started?
Oh, yeah. Let's go through that.
Okay, welcome to the APS Monday Colloquium. We are very, very excited to have Dr. Justin Deighan from LASP as our speaker today. Dr. Deighan got his bachelor's from William and Mary, and then he went to the University of Virginia and worked with Bob Johnson for his PhD. He is an expert in upper atmospheres, especially that of Mars and Venus. And today he will be telling us all about his work on EMM, the Emirates Mars Mission. So without further ado, let's please welcome our speaker.
Okay. All right, thank you, Shannon. Seems like the sound's coming through all right. All right, yeah, so I'm going to give you a summary of results from the Emirates Mars mission. This is a mission that LASP here at CU is deeply involved in. I'm currently the acting science lead for the mission, and we have some great results that I'd like to share with you today. So here's an outline of the talk. We're going to, I'm just going to tell you a little bit about the background of EMM, how the mission came to be. It's kind of an unconventional mission. Tell you a little bit about the core science of the mission, and then give you, as I said, some highlights from the past few years since it's been at Mars. And those kind of roughly break down into some primary science. And then as the mission gets older, we're increasingly starting to collaborate with other missions, finding synergies there. And also, we've had more and more opportunities to sort of go above and beyond and use the data that we plan to collect or change the data that we're collecting to do more new science. And then I'll give you a quick update on the status and the future of the mission. So, contractually obligated to say that the EMM programmatic motivation has a number of aspects. So, it's meant to be a symbol within the Middle East for sort of increasing science visibility and capability, being a catalyst for knowledge and skills for a new generation of engineers and scientists, and forming an anchor point for science and technology development. So EMM was originally conceived as basically a way to celebrate the 50th anniversary of the UAE. And to do that, the government wanted to do a mission to Mars, but they didn't really know what science would advance the field. And so they came to the scientific community and said, what should the next Mars mission be? Which is not something you usually get, a government coming to the scientists and saying, I have money, I will pay you to do whatever the next and most important science is. Fortunately, I and a couple other people in the room were part of that science definition team, and it's come a long way. Part of this has been working with people in the UAE, students, engineers, postdocs, grad students, to build up those capabilities that I was describing. And this is ongoing. But really, this is an international collaboration. So it's not just LASP here. We also have team members at UC Berkeley, at the Space Science Laboratory, at Arizona State University. We have collaborators in Europe at LMD. And as people move on to new postdoc positions, we have people in China that we collaborate with across this international team. And other places as well. So This is a nice picture of the HOPE probe before it was shipped off. This was taken over on East Campus. And so it's a pretty good sized spacecraft. We have tons of fuel left. I don't know what we're going to do with it all, but we got into orbit really well. This is just a timeline of the mission. So this was a pretty fast timeline for a mission like this. The mission concept was first developed in 2015. And in order to get to Mars by the 50th anniversary of the UAE, we were on a pretty tight schedule. In fact, that was like one of our top risks at the mission level, was not making it in time for our launch window to get to Mars. But we did, and we had a pretty nice cruise. We had a very successful Mars orbit insertion. We'd booked 3 burns to get into our science orbit. We only needed 2, hence tons of fuel left. We actually made use of that, as I'll describe at the end. And then we had our primary mission, and we're now in our extended scientific operations. And I'll say a little bit more about what's coming off of the side of the slide at the end. Okay, so as I said, I and some other folks here were part of the science definition team for EMM. And when we thought about what had been done at Mars and what the next steps for understanding Mars were, there was sort of a common theme of coverage. We know a lot of individual things about the Martian atmosphere from half dozen missions or so over the years, some of which have had varying amounts of success. But for EMM, we decided that there were 3 main objectives that we wanted to focus on. And that was characterizing the state of the lower atmosphere across a global scale with geographic coverage, local time coverage, and diurnal coverage, and looking across the seasons. Mars has seasons just like the Earth. And then we wanted to correlate rates of atmospheric escape in the upper atmosphere to those processes. Why would you do that? Well, Mars is very different from Earth in that it has had a lot of atmospheric evolution in terms of loss of atmosphere to space. Earth may be kind of an oddball in that it hasn't had a lot of loss to space compared to Venus and Mars. So this is an interesting experimental playground for planetary scientists. And then finally, we wanted to characterize the spatial structure and variability of the key constituents in the Martian exosphere. So that's also relating to escape. But really, this is all integrated. These objectives all interrelate to each other. And to do it properly, you kind of need to have these investigations that are listed here, these 4 investigations. And you can see these little arrows are tying these back to the objectives. And there's always at least some overlap. So these investigations needed to be turned into observations that we would make of the various parts of the atmosphere. And EMM does this in a way that advances over previous missions, which were typically limited in one of 2 ways. So this is some example data from Mars Odyssey. And so this is an orbiting spacecraft that measures the atmosphere globally, but it only does it at one time a day. So it's in this sort of 1.5-hour orbit. And as the planet rotates underneath, it gets to see everything, but it only gets to see it at 1 or 2 times a day, usually something in the day and something in the night. So you can build up these nice maps, but you don't have any idea. If you're looking in the afternoon, you have no idea what's going on in the morning, and vice versa. Conversely, we have many landed spacecraft, although not all of them are working anymore. But the way that those work, right, it's just like your personal experience. You sit at one place and you watch the day go by. But you really don't know what's happening anywhere else on the planet. And so these are sort of 2 end states of understanding about what's going on at Mars. And EMM's mission was to try to bridge this gap, try to see what's going on across most of the planet, most of the time, across all the seasons. And so it does this by having this huge orbit. So this is almost what you might call an areosynchronous orbit, analogous to a geosynchronous orbit. But it's a little bit offset so that it gets to see everywhere on Mars, roughly every 9 days. And it not only gets to see everywhere on Mars, it gets to see it everywhere on Mars at every time of day. And then, since it's every 9 days that we get this, we can track that from one season to the next through spring, summer, fall, winter. And so This is just an example of how that coverage gets built up. So these are little thumbnails of our infrared instrument. You can think about different local time intervals. So here's midnight to 3 a.m., noonish, back to midnight. And then the little red painted in bits are what the spacecraft would be able to observe. And you can see that over a few days, there's a lot of blue here still. We haven't seen everything. But once you get up to about 9 or 10 days, you've basically seen all conditions everywhere on the planet. So speaking of instruments, in order to achieve these science objectives, we designed a payload of 3 remote sensing instruments. So these are the Emirates Mars Infrared Spectrometer, looking in the near and thermal infrared, a little bit into the far infrared. We have the Emirates Exploration Imager, which is a filter camera with filters in the ultraviolet and in the visible. And then we have EMUs, which is close to my heart. I'm the science lead for that. And this looks in the far ultraviolet and a little bit into the extreme ultraviolet, which is some new stuff. We've never, before EMM, we did not have an orbiting extreme ultraviolet spectrometer at Mars. So this is what some of that data looks like. So EMIRS, as I said, looks in the infrared. There are a number of things it can observe at Mars: water vapor, water ice, dust, CO2. And so we're able to make these beautiful maps. This is an example of how we actually sample the planet, and then we can interpolate that to compare to models. These are some movies showing evolution of dust storms and water ice optical depth over time. And you can see that most of the planet is painted in here, which is something that previous missions were not able to do. Talk a little bit more about that when we get to specific results. So EXI is the golden child in terms of PR. It takes these beautiful pictures. So we're able to have a red, green, blue set of filters and make these wonderful color images. We're also able to look at Mars around that big orbit from a variety of angles here. You can see this is an image sequence taken as we zoom around the planet. And then we're also able to make videos of individual spots on the planet. This is evolution of some topographic ice clouds over the Tharsis mountain range. Something that is difficult for other missions to do. Basically, if you were flying over, you just zoom away again too quickly to be able to continuously take a set of images like this. But this big orbit allows EMM to observe a single location for an extended period of time. And then this is just sort of an example of how we do those color composites, combining individual images. OK, so EMUs. So as I said, EMUs is an extreme ultraviolet and far ultraviolet spectrometer. We get these beautiful spectra here spanning this wavelength range. Lots of information about atomic and molecular species. And we can make these nice videos. This is atomic oxygen going through various seasons. Those things zipping by in the background are stars. That's fun. I think that's Orion. If you see a bunch of bright stars, it's probably Orion. We also take these images of hydrogen. This is using the Lyman alpha line extending out to several Mars radii, watching it leak out into space. This is interesting because hydrogen, of course, is typically coming from water vapor. We're trying to understand what's happened to all the water on Mars. Why is it so dry today? And really, this set of images is just to reinforce that this spectrum actually, you can make an image at any one of these wavelengths. So there's a huge amount of information here about the upper atmosphere of the planet. OK. And this is just to point out that the real power of this observatory is having all of these observations from the ultraviolet to the infrared simultaneously or near simultaneously at a range of local times with a synoptic view of the planet, sort of a semi-global view. So this is just showing how on one single orbit of the spacecraft, we can get ice clouds with retrievals from the infrared. We can compare those to the visible signatures of reflected sunlight and with the XI. And then we're able to see the hydrogen at the top of the atmosphere. And so start to address fundamental questions about the water budget at Mars from the bottom of the atmosphere to the top of the atmosphere. OK, so real quick, little overview of publications. So if you're in academia, you like to chart out your publications year by year. Well, this is what that would look like for EMM. So in 2021, we started out with our documentation of the mission and the instruments. So these are all in Space Science Reviews. If you want to go read those, if you want to learn more about the mission, that's a great way to do it. Then in 2022, we had our first special issue in GRL after we got to Mars. So 13 great papers here. And this talk was originally designed to summarize all of these papers. I can't do that in a single talk anymore. So we did a big push. These were all submitted at different times. We had a little bit of a lull in 2023, but I wanted to point out that we started to have people publishing on EMM data from outside of the EMM team. So I'm going to highlight these again on the next slide. And 2024, we've been making a comeback. So we're not quite through the year yet, but we've already got a good crop of papers, and increasingly, we're getting more and more led by scientists outside of the team, which is something you always want to see with a successful mission. Okay, so I told you I can't summarize all of these papers. What I'm going to do instead is something that I did when I gave an earlier version of this talk last year in Japan. And that is to tell you about the science using haiku. So haiku is a poem, 575. There are additional rules in Japanese. I happen to have taken 2 years of Japanese, and for some reason I decided to impress my colleagues by writing haiku that was a haiku both in Japanese and in English. And so we're going to have a rapid journey. There are so many flowers. The scent is lovely. I'm not going to read the Japanese. My pronunciation I don't have confidence in, but and it would take longer. So we have a lot of results. We can't look at every single flower here, but I hope you enjoy the scent and you will remember it when you leave the colloquium. Okay, so I've taken a short set of highlights from the primary mission to start off with. We're going to start in the lower atmosphere here. And so this one is by Mike Wolf. He's the lead of the EXI camera. And this is looking at diurnal variations in the aphelion cloud belt. So Mars has a fairly elliptical orbit, gets significantly closer and further away from the sun. And when it's further away at aphelion, it gets very cloudy. And so Mike was looking at our first set of data from this season. We've got these little thumbnails of latitude and longitude. So this is your little cylindrical map of Mars. And each of these thumbnails is at a different time of day. So red, this is one of those rainbow color bars that you probably have a strong opinion about. But the red stuff is thicker clouds. The dark purple is very thin. And so you can definitely see differences through the day. We also have these across different seasons. So we call this L sub S. I'm not going to go through this in detail. As I said, this is just to kind of give you a flavor. But you can definitely see there are changes both across the day and across the seasons. And we can even sort of do these summary plots where we have season on the x-axis here and latitude. And you can see this aphelion cloud belt season where we have enhanced clouds at all times of day, and then it sort of drops off as we get later in the year. This is when a dust storm season starts to kick up and those clouds dissipate. And we can compare that to predictions from our models. And they kind of match. I mean, there are more clouds at this time in the model, but it doesn't drop off exactly the way that it does in real life or even peak at the right time. And so we have the clouds of summer in morning and afternoon, expected, I think. Okay, another lower atmosphere paper. This one's cool. So I mentioned comparing to models. Well, one thing that you might know about is data assimilation, where you take a model, you take some data that has an observable, and you try to use that to correct the model or improve the model. You adjust the model using that information from the data, and then you keep running the model. And the idea is that you're now pushing the model towards reality a little more and making it more believable. But also, you can potentially read off things out of the model that you can't observe directly, like wind velocities, for example. And so this is what you start with what you call a forecast. This is work by Roland Young. He was at UAEU. He's now at University of Aberdeen in the UK. And this is what the temperature observations from EMIRS would be. This is the analysis, or sort of adjusting the model. And then this shows you how much of a difference there was. This next figure is one of my favorite. So this is an example with the true local solar time. And then the latitude, so this is, and then temperature. So this is showing you, where it's warm at different times of day at different latitudes on the planet. Here's the observations from EMIRS. And I really want you to realize this was the best data set we had before EMM. We had these sort of very limited local time information. And now it's just on another level, right? This is amazing. This is great. And so, seeing everything, a different expectation, it is corrected. OK, last lower atmosphere result for the prime mission. So this data is so good in terms of coverage that you don't actually need a model to pull out some of the information. You can do it just by fitting the data directly. And so this is something that Sit-Tang Fan has done. He was with the LMD group in France. He's now in South China University in a faculty position. And so what he did is he looked at these temperature retrievals from EMIRS, and he was able to pull out waves in the atmosphere on the scale of the planet. These are thermal tides. So the sun rises and sets every day. It warms the planet, and the planet responds. The atmosphere has these waves that are stimulated, and they can oscillate once a day, twice a day, 3 times a day. So the diurnal mode is really strong, as you might expect. The semi-diurnal mode is also pretty strong, but Sit-Tang was actually able to pull out the terdiurnal mode, which has been kind of tricky with previous data sets. You really need that really good coverage and sampling. He found, comparing this to the global climate models, generally good agreement in the amplitude, but one interesting thing is that the phase is different. So the atmosphere was not reaching peak and minimum densities at the times that the models predict. That's interesting because we think those are modulated by things like wind speeds in the middle atmosphere, things that are very difficult to observe directly. And so this shows that we're getting information that will really help us improve those global circulation models. And so the poem here is, the tide is rising, but this is not the right time. There are 3 waves. All right, let's move up to the upper atmosphere. This is a little closer to my heart. I've got a few results here from EMUs. So one of the things we wanted to do was map the planet in the far ultraviolet. And sure enough, we did that, and we saw all these crazy structures in the air glow. This is air glow that's stimulated by extreme ultraviolet from the sun, breaking things apart, energizing stuff. It glows. We look at it, and we see these blobs of oxygen. We see blobs of carbon monoxide. What is going on? Dynamics. So these things get shuttled around in the upper atmosphere depending on circulation patterns. They kind of clump up on the night side and then rotate around onto dawn. So very, very rich set of information about the globally integrated circulation of the planet. And so this is work by Scott England at Virginia Tech. And the takeaway here is how rough this sea is. But know that morning is bright. The horizon, too. OK. Now, these are a couple of much more recent results. These are published this year from some of our postdocs here at CU LASP. So this is work by Susar Laragaram. And he's been looking at the hydrogen and its variation through the year. So one of those neat things about EMUs is that it can see the Lyman beta line here in hydrogen. That's something that no previous orbiting asset could observe. There have been a couple flybys, but that was about it. And of course, the Lyman alpha is very bright. And so Raghuram was able to map these out across the seasons. And he found, as we had inferred from other previous data sets, both from ultraviolet and other methods, that during the southern summertime period, this would be northern winter, there's a massive expansion of the hydrogen that surrounds Mars. And we believe this is due to changes in circulation that allow water to get up to altitudes where it can be broken apart into hydrogen and oxygen, and the hydrogen floats up off into space. This is important for understanding that loss of water over the history of Mars. So There's even a couple of bumps here that don't quite follow that seasonal trend. Those are probably driven by sort of short-term changes in circulation due to dust storms. That's very much an open question area of active research. So very exciting that we have the coverage we need to consistently map this out. And so this leaking water, it changes with the seasons and then disappears. Okay, so I said the water floats up, hydrogen, da-da-da-da. Okay, what happened to the oxygen? Well, we see the oxygen as well. This is work by Krishna Prasad, or KP as we call him, looking at the oxygen observations that go along with those hydrogen observations. We're able to observe to much higher altitudes than previous observations. That's important because we think it's those higher altitudes that are most associated with the oxygen that's escaping from the planet. This oxygen comes from ion photochemistry in the upper atmosphere. So it's a very energetic process, and it varies with the sun, with those solar inputs over time. So KP was able to map that out and then make a plot of the expected variability versus, due to the variability of the sun, with the actually observed variability. And sure enough, he gets a super high correlation. Awesome, we know how everything works. Okay, maybe not, but it's good. The basic physics that we expect are there, sure enough. And so, a blast of scorched air. It was seared by a light from above the sky. This one's more ostentatious because this is what I do. This is my bread and butter, is hot oxygen. Okay. All right, so that's sort of what EMM went to do, but it's done a lot more. So I want to tell you a couple of things, synergy that we have with other missions. And then I'll kind of tell you about some above and beyond things we've been working on. Okay, so this is some work by Aurélien Stickerbinin, don't ask me to pronounce it. But he was with us at ASU. He's now in France, in Toulouse. And he is looking at comparing data from the Trace Gas Orbiter, which is an ESA mission, looking at their solar occultations, where they're able to determine the particle size of water ice aerosols in the atmosphere. And so this is just ACS data where he's showing that as a function of latitude and altitude, where they do see ice particles, they tend to be larger low down and smaller high up. That's pretty consistent with our experience on Earth, right? The low down clouds got these big particles, they're really optically thick. You go high up, there are these cirrus clouds that are thin, wispy things. But the reason that Aurélien's looking at this is because when we take those beautiful pictures with the EXI camera and we try to infer how thick the clouds are, we have to make a number of assumptions about the clouds, about the dust. And so what he did is he went and he found a bunch of times that TGO was observing the same spot that EMM was observing. So we have a picture of the planet from EXI, we have a scan from the side from TGO, and we're able to put those together and test some of the assumptions that we would typically make. And so this just shows some of the things that Aurélien looked at. He tried putting in the exact conditions observed by TGO and doing the EXI retrieval. He tried using a generic profile. He tried playing with where the dust was. And this is really useful because you don't usually get to do this kind of experiment, certainly not with a single spacecraft. So this is sort of the power of having multiple operating spacecraft looking at the planet from different points of view. And so, secrets of the clouds, from above and from the side. Just how large are they? All right. Another good example of synergy between two missions is this work by Mike Chaffin. So I mentioned that we saw this crazy structure on the day side of the planet. One of the things that we saw were these patchy emissions in the hydrogen lines. And we immediately recognized this as being some kind of auroral process. This kind of thing had been seen before at Mars, but we never had images like this where we could view what was going on in a global context. We just had little snippets of one place or another. And so Mike was able, by using data from the MAVEN mission, which many of you are familiar with, also a big deal here at CU, he was able to combine data from MAVEN and EMM to interpret these. And so what we believe is happening is that the magnetic field, the interplanetary magnetic field, is, well, in some cases, it is going into a unique configuration that allows the solar wind to more directly interact with the planet. In others, it's not so obvious, but it's not so obvious why it's happening on that particular day and at that particular time. But you wouldn't know that these were different situations unless you had that data set from both missions. And so again, this is the power of having multiple missions making complementary observations. And so the wind is blowing. Breaking waves are made of light, like gold-filled fractures. Okay. So I think most missions, as they go on, you start to realize things that are hiding in the data that you didn't expect, or maybe you expected, but you learn some surprising new things. You also learn to teach your instruments or your retrieval algorithms some new tricks. So this is, it's that time in the presentation. So one of the most obvious things is, well, just take data more frequently. So we came up with a mode for the EXI camera where we took images of the planet every half hour instead of our usual cadence of every few hours. We at first tried taking data every few minutes. It was too fast. There weren't very interesting changes. But at a half-hour cadence, it's a manageable amount of data production, and you see some really cool stuff. This is a result published by Klaus Gebhardt. He's a professor at UAEU and a collaborator. He's a technically a participating scientist on the science team. And so he found this neat event where in the morning we see these Lee waves behind Lyot Crater here in the northern hemisphere. And then as the day goes on, this dust storm erupts. And then we kind of lose sight of it in the afternoon. But clearly it has grown dramatically just in this few-hour time period. This is something that no other mission could observe. And so there's some sort of dynamic modeling to explain why this might have been happening. But this shows how these higher cadences can enable new science that you wouldn't be able to do otherwise. And so, dust storm arising, like ripples in the ocean, more and more murky. Okay, another lower atmosphere sort of stretch goal here. This is work by Sam Atwood. He was one of our postdocs with Khalifa University. He's now at NASA Goddard Space Flight Center, some combination of those words. And what he did is he was looking at these infrared spectra that they do the retrievals on, and he noticed that sometimes there were discrepancies between a best fit sort of assumed set of aerosol parameters and what Mars was really doing. And he realized that by varying the size, the effective size of the ice particles, he could actually do an enhanced retrieval where he pulled the ice particle size out of the data. And so he was able to do this for a large data set. This was just published a couple months ago in August. And you can see here, this is the total ice optical depth. And this is the effective radius that he pulls out. And you'll notice that it's very highly correlated, right? Where there's a lot of water ice, those particles are larger. That's pretty typical. If you've got more water, it's easier for those particles to accrete and get bigger and bigger. It's not a complete one-to-one correlation, though. Part of that is related to the water condensation level. It depends on whether these particles are condensing close to the surface or high up at altitude. And so that also became apparent in Sam's analysis. So this is just the regular data we plan to take, but as you start to notice the quality of the data and what it's telling you about the planet, we can improve the science return from the mission. And so, the voice of color. Are they really so tiny, those pieces of ice? Okay. This is something that I think is really cool. So with the EMU's instrument, one of the things that we saw was aurora. This is not something that we had built into the mission operations, but we had kind of expected to see it because previous missions had seen aurora. The wrinkle was that no one had seen aurora in the far ultraviolet before. But sure enough, in the EMU's data, it just popped out right away. So we've had a number of publications on this, and it's culminated in this idea that we can look for very short-term variability by taking the instrument and staring at one place on the planet. This is enabled by the high sensitivity of the spectrometer and that really big orbit of EMM. Remember, like with the dust storm, we can stare at this one spot for a long period of time. We can do the same thing with the aurora. So what I'm showing here is these scans of the planet during various space weather events, or lack of space weather events in some cases. And then in the center, this little narrow strip is what we're able to see by staring with the spectrometer. And so you can see that sometimes we get this sort of pulsing action. Sometimes there's these blobs that sit here. Presumably they have some constant stream of energetic particles that are just flowing down into the night side atmosphere. We also see these long skinny features that are undergoing some kind of dramatic evolution. We get like this sickle shape starting out, and then it starts wandering across the planet. Remember, this is thousands of kilometers in size. This is just, if you were on North America, watching, you would just see this aurora sweep across the whole country in like 20 minutes. What's doing that? Well, it's area of active research. One of the other papers published this year looks into this a bit more. And then finally, we have these more extreme solar weather events where solar energetic particles rain down over the whole planet. Extremely dynamic. But again, we've been looking at other data sets from MAVEN, for example, and we can see things turning on and turning off in the way that one might expect when these solar particles arrive. And so, there, a tea kettle. Light fills it up to the brim. It bubbles and boils. Okay. I'm going to tell you now about a cool thing we did last year. So we got this big orbit with EMM. It turns out we get really close to the moon Deimos. This is the outer moon of Mars. It's been relatively little explored because it is so far from Mars. And all the observations have been from satellites closer in looking outward. So we don't know very much about the anti-Mars facing side. But as part of, towards the end of EMM's nominal mission, we did a series of flybys. So we used some of that massive extra fuel that I described to tweak the orbit just enough to fly by Deimos. And so what we have here is a set of images captured by the EXI camera during the closest approach that we had. This was in March of last year. And Mars decided to photobomb in the background. We knew that was going to happen. And then off we go again. Now, this image sequence, as I said, is from EXI, but we actually did have data being collected by all three instruments. And so that sort of powerhouse of full spectral coverage from the ultraviolet to the infrared could be brought to bear. And we have thermal inertia information from the infrared instrument. We have some spectral information and high-resolution imaging of craters from EXI. Also, there's phase angle information. And then from EMUs, this is a two-color image of hydrogen from the universe reflecting off of the moon, and then direct sunlight. And so there's hints that this is actually a very useful data set in terms of being able to tell us about the origin of Deimos. It's currently unknown for sure whether it is a piece of Mars that was launched into orbit or whether it's a captured asteroid. Similar open questions for its fellow moon Phobos, which is much closer in. There are hints from this data that it is in fact a piece of Mars, but that's an ongoing story, and it is also benefiting from this intermission dialogue that we continue to encourage. And so, you gloomy boulder, where is it that you come from? You are so quiet. All right, So I'm going to wrap up here with a little bit of status and future. So EMM continues to explore the global dynamics of the Martian atmosphere, and our data set is now covering multiple Mars years. The HOPE spacecraft and all 3 instruments are healthy, which is great. That's basically a requirement to keep doing good science. And encouragingly, the UAE Space Agency has approved extending operations until March 2027. So that is 4 calendar years after the end of the original nominal mission. So, of course, as missions go on, there's some belt tightening. We have simplified the observation scheme that we have, but we've done it in a way that attempts to retain as much of our core science as possible. There have been some hiccups in this during the year, so we have some outages, but I'm glad to say that we're currently operating nominally and we're taking good science data. And finally, support for science analysis has been ramping down. And we're no longer doing additional development of the higher level products. However, the products as they currently are will continue to be published. And so you can check out our Science Data Center here. We currently have things published through the end of February of this year. And the ASU team has done a great job getting a lot of this data into the JMARS program, in case you're familiar with that. It's a way to visualize, well, basically all the available data sets that can be mapped down on Mars. So we're looking forward to the future of science from EMM and increasing that involvement with other missions and also from the rest of the community. And with that, I will take any questions.
Thank you, Justin. And I have a haiku prepared on behalf of the department as a thank you. Words that inspire us, wisdom shared with APS. Thank you for your light.
Honored.
With that, do we have any questions for Justin?
Thanks, Justin, as always, for a fabulous talk. I would like to know if Emir saw anything interesting in the IR spectra of Deimos, if you're at liberty to say, or if there's a paper already, please tell me the paper.
Yeah, so there isn't a paper yet. We've had a couple of conference submissions on this. And what is really interesting about it is comparing it with Phobos, because they are pretty different. And the most basic takeaway is that they really look more basaltic than carbonaceous or typical D-type asteroid, which is previously sort of the best hypothesis. But that's not much of a hypothesis because D-type asteroids are just weird. Yeah, the basaltic component is one of the strong pieces of evidence that it's Mars. There are differences in weathering between Phobos and Deimos. And if I remember what Christopher Edwards told me correctly, Phobos seems to look fresher. And the idea is that it may be undergoing more tidal stress because it's much closer to Mars. And so there's some continual resurfacing processes that may be going on there. Whereas Deimos, being much further from Mars, we've seen that basalt be space weathered pretty consistently for however long it's been out there.
I wanted to ask you, lovely haikus, love it, beautiful, great fun. What would you say coming out of this mission, what do you would love to do with the next mission? If I could give you the money to do a discovery mission, what would you do next?
Why did I not anticipate this question? So one of the things that kept coming up during the development of EMM was our orbital dynamics design lead, Jeff Parker, would say, this is the best we can do with a single spacecraft. And so I think that's it, basically. You need a constellation, or at least multiple spacecraft.
How many?
Okay. Probably more than you can afford, but if you're being the space ferry, I mean, 3 would, in principle, get you complete coverage if the orbits are large enough. There's always going to be questions, and this is in a remote sensing context, right? Because remote sensing, you're always going to get the most coverage from that. With in situ, you got to be down in the soup, and you're sampling where you're sampling, and adding 100 more samples in situ will always get you better. But for remote sensing, for global, if you're in a big orbit like this and you have 3 of them, you're basically seeing everything everywhere all the time, or at least it's possible.
Yeah. Yeah, can you go back to the slide that shows Lyman alpha and beta and gamma?
Yeah. This
Before
was,
the haikus, yeah, right.
Yeah. That would be this one?
Yeah, that. Okay, you didn't explain on the left-hand side the green, the yellow. Why is the yellow line, the Lyman alpha, very broad? What's going on?
So I cut this down from a larger figure, so let me orient myself for a second here. But these are foreground observations. So we take both foreground and background observations. We have to subtract the interplanetary hydrogen from it.
Yeah, sure.
And so these, however, are foreground. So it's a combination of the Martian corona and the background on the sky. And the main difference between these two is this L sub s. So this is the season. So the green line is from aphelion, when Mars is furthest from the sun. And the orange is from perihelion, when it's closest to the sun. And much larger than a simple geometric effect, the hydrogen lines have gotten much, much brighter. And so this is interpreted as an actual increase in the hydrogen corona. And it's not just a thermal increase. It's not like you just pumped up the temperature and the exosphere expands. It really is a larger supply of hydrogen at that time.
Okay.
Could you comment on the cultural aspect, especially how this has worked out with a Middle Eastern country?
Yeah, I mean, that's a really interesting question. Obviously, there were sort of social aspects to that. And I think that the teams from various parts of the world did a good job of trying to bridge whatever sort of differences existed on social levels. There were some things, there are certain sort of groups, eating habits, for example, that we learned about. But it was actually a really, one of the parts of the mission that I've enjoyed is the cultural exchange. We did a number of field trips in the UAE going out into the desert. I mean, I learned more about Middle Eastern culture than I did before, that's for sure. I think our Emirati colleagues were also exposed to a lot of things coming here. A lot of them came and worked and lived here in Boulder while the spacecraft was being developed. And they were exposed to a very different culture from their own. And I think a lot of them brought that back, both a professional culture and sort of a social culture. You know, taking them up, doing hikes, eating out. You know, it's been really interesting from that point of view. From a purely sort of professional point of view, before this mission, there really wasn't much of a science culture, certainly not a space science culture in the UAE, which was really interesting to walk into that and have a bunch of people who are competent engineers, and they have the basics of physics and chemistry and all that, but they don't have an environment in which they can just jump in and do space science. There were no graduate students doing this. There were no postdocs. And so that culture developed integral with the mission, which has been very interesting to see play out. And when I go there now, I haven't gone recently, but when I was there last year, there are all of these college and graduate students there who were high school students who, you know, I met as RU students who came over here or met them doing outreach in the UE, and they are so hyped about doing space science. They want to be a spacecraft engineer, or they want to learn how to, you know, make discoveries about the universe. And I think in that regard, this mission has been extremely successful. One of the remaining challenges, I think, for the UAE is to continue to cultivate that beginning that they have created. And it remains to be seen how that will play out, but I'm happy that there's the EMA mission, and there's other continued interest in space science in the UAE, because I think they have created an opportunity, and I hope that they will take advantage of it.
Thank you so much for all of this. I'm imagining your data in the exoplanet context, where the very best that we will ever hope for is a spectrum, maybe a time variable spectrum of a point of light, and even that's decades away. I'm curious how, like, have these data been, like, you have been looking at them in beautifully spatially resolved detail, but is there a, like, panchromatic spectral energy distribution of Mars that one could get their hands on these days? Like, you have this, you have your patch in the UV, you have imaging in the optical that presumably could be interpolated, and then you have your IR spectra. I'm asking both from the perspective of, like, in the cosmic perspective, our textbook, there's a very cartoony spectrum of Mars that would be lovely to have in real data. But then also from the exoplanet perspective, both in kind of planning our observations, I have often lamented that it's hard to place kind of these, UV observations we might be imagining in the context of thermal IR as well. So.
Right. So we haven't done an integrated product like you described. However, I noticed looking through the AGU abstracts that Sitang, who had done that tidal wave analysis, is collaborating with some colleagues in China to do exactly this. So there's an AGU abstract on exactly this topic. So I would say go take a look for, like, Emir's exoplanet in the search, and that will tell you more than I can right now. But people are starting to think about this, and I do think it's a good data set for thinking about these kinds of things. Dave.
Okay, a question and maybe a comment if you'll indulge me. So the question is, when you outlined the 3 objectives for the mission, the one in the middle, B, is kind of connecting lower atmosphere to upper atmosphere. And I wondered if you can talk more about what EMM has contributed there. I mean, there's the wave analysis from Fan.
Yeah, there's that analysis from Sitang. One of the interesting things that he's been working on, so if those waves are driven from below, they will have a certain tilt. Part of my answer was going to use this slide, but I've started already on Sitang's stuff, so I'm going to have to continue with that. Okay, so you see how these have this sort of tilt with local time and pressure level or altitude. So that tilt is in part driven by the fact that these waves are typically driven from below, from the lower atmosphere being heated and cooling at night. However, during some seasons, especially during dust storms, Sitang has noticed that reverses, which implies that there's actually more heating happening high up in the atmosphere and changing the circulation. And so that is one aspect that EMM is able to make unique contributions to our understanding of under what conditions do we have more forcing from the upper atmosphere versus the lower atmosphere driving the circulation and the thermal state of the middle atmosphere. And that's definitely in the vein of Objective B. Another thing I'll mention is the slide that we were just on. So I mentioned, so Raghu put this nice little arrow here at this bump. There's also other bumps that your eye might see in this timeline. And we've been able to identify some of these as being related to dust storms. So these are case studies, basically, of a perturbation in the lower atmosphere due to a dust storm that changes the circulation, changes the vertical distribution and composition of the atmosphere, and we can see the effect in the escape of material from the planet. So that also gets to Objective B. I think other than that, those are some very specific things. We had kind of hoped that we would see some big flares or something with EMM. Unfortunately, the biggest flares in the past couple of years, we were turned off for one reason or another. It just happens sometimes. But as I said, we're taking data now. We're taking data very frequently, and the sun is continuing to be active, so we're hoping to see more of those kinds of events going forward.
Okay, thanks. I won't do my comment except that Andrew asked about cultural things that we noticed, and I have a couple others to share, maybe offline sometime.
Yeah, that would be good. Dave had my job before I had my job. So.
Very excited.
Sorry, what was that? Yes. Yes. So you might have thought that we would have a very male-dominated UAE science team. That has definitely not been the case. So the vast, vast majority of our science team members on the Emirati side have been women. Our science leads, Sarah Amiri and Hessa Al-Matrushi, before I had to step up from the deputy role, both women, computer science engineer and electrical engineer respectively, who took on the role of doing science. We had, I mentioned, we were training other engineers to do science. We called that the, what was it? The science apprenticeship program. And yeah, we had sort of one guy and like 6 ladies. A lot of the RU students were also women. A lot of the men who came over did great work, then went back and they said, well, space science was cool, but I'm gonna go do this startup. I'm gonna make an app, or I'm gonna get into oil industry because, you know, that's what my uncle does, or whatever. The women have an interesting social situation where they're able to do this because they want to do it. And they are, in my experience, and the experience of the mission, they are given the opportunity to do that. And as a result, they have done it.
Got 2 more over here.
Great talk.
Thank you.
I was curious when it comes to the aurora, if you can say the 3 different types of aurora that are not caused by, well, I don't want to say not caused by a solar event, but not, you know, some massive solar event that excites most of the atmosphere. When it comes to the hydrogen and oxygen escape that those 3 types of aurora might cause, is there a significant contribution as an escape mechanism that these aurora can cause, or is there one type that might be more efficient at driving escape?
Yeah, so the aurora themselves are usually not a very large part of the upper atmospheric energy budget. If I just go to this one. So this side, this crescent here, in case I hadn't mentioned it or you didn't figure it out, this is the day side of the planet. And then this is the night side, right? And this is oxygen emission. So the oxygen in this case is just getting slammed with energetic electrons for the most part and then glowing. It's possible that there's some small amount of escape just because you have highly energetic processes going on there, but it pales in comparison to the normal day side process. However, the aurora are useful in that, you know, they show us when you have large amounts of energetic particles interacting with the atmosphere, what does it do? How does it respond? And that's probably going to be more important maybe for the early solar system when we think Mars lost most of its atmosphere. And instead of this nice calm solar wind that we have a lot of the time, the early solar wind in the solar system was probably extremely turbulent with storms basically all the time. And so then you would have conditions more like this, where the solar wind is able to frequently but highly variably interact directly with the upper atmosphere. And then the story is different. Then you're really talking about more energy going in and possibly enhancing escape or changing the way that escape occurs from what we observe at Mars. And so observing the aurora today can help us understand that physics and model those conditions.
Thank you. And last question.
I just wanted to make you walk all the way over here. Yeah, this is really interesting science, but none of it would be possible without the spacecraft bus. This is a little odd question. My understanding is that was built at LASP as well.
Yes.
And so are there any lessons learned, and are there possibilities in the future for building other things like this?
Yeah, absolutely. I think some of the spacecraft team has joined us today, which is awesome. Yeah, Jimmy's back there.
Wave to the back row.
Yeah.
Thank you, guys.
Yeah, thank you for your service. None of this would have been possible.